Let's just do another example together. Find the partial fractions decomposition of this thing. So the first thing to notice is that the degree of our numerator is larger than the degree of the denominator. So whenever that is the case, we need to go ahead and divide. Actually, let me stop and say for a second. I recommend that you, when we go through an example, you can pause, try to do it yourself, and then watch the solution to double check. So you go through the division. X squared into x cubed gives us x. That's x cubed minus 3x squared minus 10x. So that's convenient. That happens to knock out both of those first two terms. There are that x cubed minus x cubed is 0, minus 3x squared minus negative 3x squared is 0. We have 2x minus negative 10x, and then drop down to 5. And we're done dividing already. So our result is x plus our remainder over our divisor. Okay. So then this x is just going to chill out. That's going to be part of our final answer. Our final answer will be x plus something. And then we do partial fractions on this thing right here. So we factor the denominator. And then we want to split that up into fractions, where each factor is the denominator of one of our fractions. Multiply through by the greatest common factor. And remember I said that when all the factors are linear, it's easier just to plug in specific values of x. So I'll go ahead and plug in x equals negative 2. That gets me negative 24 plus 5, which is minus 19. And then that's negative, this is 0, and negative 2 minus 5 gives me negative 7. Oops, not a, negative 7 times b. So then we get b, it's 19 over 7. We plug in x equals 5. What do we have? We have 60 plus 5 is 65. Then we have 7a, and that's 0. So we have a equals 65 over 7. Now this isn't a nice looking fraction, but that's okay. We can still go ahead and write our answer. A is 65 over 7. So the way we write that, we don't want to put a fraction within a fraction. So we say 65 over, stick the 7 in the denominator, and then write the factor just like that. We get our partial fractions decomposition. Now, oh yeah, and then I almost made a silly mistake that you all will make too, that this was the partial fractions decomposition of this part, but we still have this x floating around from before, so that needs to be part of our answer. I'll just left that out. Now the handy thing about partial fractions decomposition is that you can always check if your answer is correct. If you go to your calculator and plug in the original equation, that's my original equation, and then plug in my answer, they should be exactly equivalent. When you do partial fractions decomposition, you're finding an expression that is just it's a rewriting of the original expression. It's not a new one. So if I type in the original equation in my answer, I should get the same thing. And let's see if I've done this correct. I can go to my table and look at that. All the values are the same all the way down the line. So I have done it correctly. Yay. If you got different values, even if they're close, if you get different values for y1 and y2, that means you made a mistake somewhere along the line, and you need to go back and fix it. Right, now we're going to look at what happens if our denominator has repeated factors. If our denominator has repeated factors. So let's say we want to find the partial fractions decomposition of this thing here. Say 4x over x minus 1 cubed. Now you might think, hey, we're done. There's only one factor in the denominator, but that's not actually true. in order to do calculus things, we need the degree of the numerator to be 1 less than the degree of the denominator, which is why we will need to split this up. So now, in general, when you have an x minus 1 cubed, if you added something up and got x minus 1 cubed in the denominator, that means you could, if that's your least common denominator, you could have something over x minus 1 plus something over x minus 1 squared plus something over x minus 1 cubed. So you need to set up each of those fractions and then solve for the missing parameters. So just like always, we multiply through by that least common denominator, x minus 1 cubed. And the first fraction, one factor of x minus 1 cancels, leaving us with x minus 1 squared. In the second fraction, two factors of x minus 1 cancel, leaving us with just x minus 1. And in the last fraction, all of them cancel, leaving us with just c. Right? Now, when you have repeated factors, there's one thing that, well, this is a case where it might be handy to do a mixture of our two methods. Sometimes we expand and equate coefficients. Sometimes we plug in values for x. In this case, it can be helpful to do a mixture because you notice it's easy. If we take x equals 1, well, that's going to cancel out some stuff. So on the left side we have 4. On the right side we have just c. So right away we get c is 4. But now there isn't another convenient x value to plug in. So then it might be handy to move into method number 1 of equating coefficients. So if we expand here, 4x equals a times x squared minus 2x plus 1 plus b x minus b plus c. So gathering all of our terms, we've got an ax squared, we've got a minus 2ax, and a plus bx, and then we have a plus a minus b plus c. Okay, so now over here, we've got an ax squared. On the left side, we have no x squared term. So if we look at our coefficients of x squared, on the left side we have 0, and on the right side we have a. So a, it turns out, is going to be 0. And then we just have b remaining to solve for. And since we have a and c, we can use any part of this. But if we take the linear term, the x term, we have 4x equals minus 2a plus bx. So that means 4 is equal to minus 2a plus b. We know a is 0 from before. So then we get that b is also equal to 4. And then our partial fractions decomposition. A is 0, so that's totally gone. And we just have 4 over x minus 1 squared plus, and c is also 4 over x minus 1 cubed. And we should go ahead and check that answer by plugging our original expression and our answer into our graph. And go to our table, and we can see, oh, look, they are all the same, so we have done this correctly. So that is our correct answer here. So if you have repeated linear factors, you start with the factor once, and then you keep adding powers all the way up until you get equal to the power you have in your original thing, and you've got a over that plus b over that plus c over that, all the way through all the powers that you have on your factor. Now there's one more type of thing we haven't dealt with yet, and that's, if you go back to the beginning of the notes, this number 4 here that we haven't dealt with yet are quadratic factors. Now I want to pause here for a second, because in this problem right here, it looked like we had some quadratic factors. This x minus 1 squared is a quadratic, right? But there is a distinction in terms of doing partial fractions. There's a difference between a linear factor twice and what it might be an unfactorable quadratic. Okay, so if we factored our denominator and got, say, x squared plus 1, we can't factor that into real linear factors. So we have to do something a little bit different, and that's different than if we have a linear factor times another repeated linear factor. And partial fractions always works on a rational function because every polynomial can be factored into linears and quadratics. For our purposes, we'll only deal with, equations that can be factored into fairly nice linears or quadratics. There won't be any coefficients that are like 2 plus root 5 over 3 or anything goofy like that. But in principle, you can do this with any rational function. So with quadratic factors, in the denominator you have your quadratic that cannot be factored. And remember, when we do partial fractions, we want the degree of the numerator to be less than the degree of the denominator. And so if we have a quadratic in the denominator, then in our numerator could be linear. So if this is a second power, the numerator could be first power, which means that we need to have a general expression for a first power equation. So we write ax plus b, or it doesn't have to be a and b, but something times x plus something else. And then if there's another quadratic factor, we go cx plus d over that quadratic factor, and so on and so forth. Yeah, as far as we need to go.